Great. So thank you for having me, Nina. I'm super excited to be here. I'll be talking about machine learning in production, specifically around the debugging parts. Let me move forward. I have a lot of content that hopefully I will try to get to all of it, but maybe not. We'll see. Please feel free to ask questions at any point in time. I'll talk a little bit about production ML pipelines, an overview from both like a people and collaboration perspective, as well as the systems and architecture perspective. I'll go through a small case study of training a model, getting good test set metric, and then what happens after deployment or simulating that kind of deployment, some challenges around that, and then hopefully motivating areas of future work for everyone. Again, please feel free to interrupt with any questions at any point in time. I think the chat should be enabled. So great.
Yeah, the chat is enabled. And yeah, just everyone, please send your comments in the chat. And after the talk, we will go through each question and yeah, we'll have the Q&A session.
Sounds good. So a little bit of background on myself. I studied at Stanford. I did my undergrad and master's in computer science, focusing on systems and AI respectively. I also did research in adversarial machine learning, specifically around adversarial attacks and robustness of computer vision models at Google Brain. After school, I went to an applied ML startup as the first ML engineer, working with a lot of time series data. And I got a very nice role because I was both working on these machine learning methods for time series data, as well as building the infrastructure for a lot of people to collaborate on large scale machine learning algorithms and data analytics. And maybe it's a commonly known thing, but at startups, your role kind of is all over the place. I did a lot of stuff in both engineering, product, and recruiting. And I learned a lot from it. It really motivated my current interest in production ML, which I'm very excited to share with you today. A little bit of background on ML and applied ML in general. I think there's a lot of talk online now, which is great, around how a lot of data science projects don't make it to production. Specifically, what that means is maybe like a researcher and a data scientist will look at a data set, try to fit a model to it, get something out of it, but they won't actually be able to get any use out of it or deploy it in production in their industry code base. And this is kind of sad for a lot of reasons, but it's also motivating. Like, why is this the case, right? And there's a lot of reasons. Maybe like one common one is that a lot of real world data is not necessarily clean and balanced like a lot of the canonical benchmark data sets that we do research on. The real world data is also always changing, especially time series data. And bottom line is, as I'll show today in this talk, right, showing high performance on like a fixed train and validation set doesn't necessarily mean you'll have consistent high performance when that model is deployed. So my interest has kind of evolved around robustness and just making ML that works in the real world a lot over time. In an academic setting, I was very excited about deep learning robustness, adversarial robustness in particular. So that could involve fairness, generalizability to unknown distributions, ML security. But in industry, really, when I joined a startup, I realized that it's very different. In academia, we train a lot of models and we try to come up with great methods, robust learning methods, maybe. But in industry, we don't want to train models all the time. We want to do as much inference as possible. And that brings up a whole host of new problems, right? What happens beyond the validation or test set? And hopefully that's motivating enough. Today, I won't be talking about how to improve model performance or how to do data science, feature engineering. I'll assume basics or familiarity of ML algorithms, but please interrupt me if you have any questions. I will be talking about kind of what is the collaboration like behind building ML systems and pipelines to deliver business value. What are the components, like at a systems perspective, of these production ML pipelines? Modeling is just one small part in that pipeline. And then a case study of challenges faced post-deployment. I hope that this is subtly motivating ML ops as a discipline. There's a lot of great work out there around this, but without further ado, let's go. Okay, so overview. of ML pipelines. As I mentioned before, right, modeling is just one part of the pipeline. And that modeling part, right, can be owned by an ML practitioner or data scientist. A lot of people collaborate when it comes to any like applied ML project in industry, which I found very different from in research. There's just a few people that are on a paper. I don't know, maybe these days in machine learning, there's like 10 authors on a paper. But really, who's writing the code? It's one or two people. And those one or two people are the only ones familiar with that end-to-end code base. But in industry, right, there's lots of stakeholders and many technical dependencies. There's data, changing models, changing evaluation metrics or criteria, selling this, mapping the metric to ROI, all of these unknown problems that require a lot of collaboration. And a thing about this is different stakeholders speak different languages. When I was in research, I was working a lot with other computer scientists or ML researchers, but when I was at my job, I was working with product managers, data scientists, clients who may or may not be technical from a machine learning perspective. We don't know. And the other thing is, especially in applied ML, I found that domain experts are very key. I was working on ML for cars, specifically vehicle sensor data, and predicting whether they would fail or components of those cars would fail. And I'm not a mechanical engineer. I don't know anything about cars, but there are a lot of people who can come up with good feature ideas. Another big issue in these like production ML pipelines is that there are lots of changing data and business requirements, especially with time series and sensor data. Who knows what'll happen? Maybe the weather hits, I don't know, so it starts raining, something happens, data looks different, changing business requirements. Maybe a new kind of model or car comes out, and then all of a sudden everybody's priorities are shifted. How do you focus on that? Open question. And the thing that makes this challenging is the model developer specifically, or the person who's responsible for modeling, has to be up to speed with all of these changing data and business requirements, even if they don't own it. And that can be complex, especially if you're trying to transition your project over to someone else. And bottom line is, in industry, models are treated as software, which is its good and bad components. With software, right, like we've come up with frameworks to iterate on it and figure out how to get value from it and transition it over to people whenever somebody who owns the project leaves or switches to a different team. This is very hard to do from an ML perspective. Imagine training a model and working on that for a year and then switching companies. It just seems daunting to onboard somebody to this kind of project. And I found a diagram from the Introducing ML Ops book that really does justice for all these different kinds of stakeholders involved, and looks complicated, is kind of complicated. But at the end of the day, I think the real takeaway from this kind of diagram is so many different stakeholders are involved. And data scientists right here are the people responsible literally for the modeling in particular. So if anything goes wrong in any of the other boxes, or anything changes in any of the other boxes, or any of the other people's responsibilities, it all boils down to how do we fix our pipeline. I will look for any questions now.
Yeah, we have a question from Das.
Do you want me to do them in the Q&A, or do you want me to just do them now?
Maybe just to make sure that we're on time with the presentation, we can leave them for
Q&A. Okay, perfect. Yeah. Sounds good.
That's okay with you.
Yeah, great. So, yeah, TLDR here is that the people overview can be very complex, and it's open question, and how do we get all of these people to collaborate? And I took a stab at making my first flow chart of life cycle of an ML project. I want to emphasize the aspect here that this whole modeling and iteration part is a cycle. And the part that should not be part of the cycle is aligning on the metrics. Too often I have worked on applied ML products on industry where the metric or what the client cares about is changing regularly, which makes it very, very hard to compare like different versions of the project, right? Whenever you're trying to build an ML model, for example, you want to establish some sort of baseline and get incremental accuracy. or incremental metric performance. But it's very, very hard to do if you haven't fixed that metric in the beginning, whether that be like a precision or recall or F1 or accuracy. Those are classification metrics. I don't know, whatever metric it is. And another thing that I've found is a lot of times in these applied ML projects, it's not immediately clear how the metric maps to money or ROI. And maybe that's part of this like research and data science exploratory culture of we look at a data set, we get extremely excited and we try to solve some hard problem with the data set. But at the end of the day, right, if it doesn't have any business value, that can be very hard and disheartening whenever it doesn't make it to production and isn't sustained. Okay, so that was mainly lifecycle of an ML project. Moving over to the technical system, right? That was one ML project, and companies will have more than one ML project ideally. Ideally, they have lots of data scientists who are working on different projects and they can sustain them over time. How do you build a system to accommodate all of these projects? And this can be very hard. Every company has done it differently, and I think Uber has a great series of blog posts around Michelangelo, which is their kind of infrastructure for, or their machine learning platform. At a high level, as talking to people in my own experience, the whole infrastructure and pipeline for ML has multiple components, ranging from ingesting data to outputting some predictions or serving some model. When you ingest data, it'll go into some sort of data lake maybe. We'll have some process called ETL that will do some feature transformations, extractions, whatever, and dump that in a feature, also cleaning is an ETL maybe, and it'll dump these features in a feature store. And this is kind of like the central, think of it as like the central code, central base of all the features for a lot of data scientists to use. And that from there, right, you can fork off into multiple different data science projects, my bad. And this diagram, this batch training job shows like, maybe this is one kind of training algorithm or training job. And then you can dump the model somewhere, serve it somewhere else, monitor the job performance. I think the thing that I want to emphasize in this two things I want to emphasize in this diagram. One is that offline training and evaluation is different from the online or live predictions, both from the infrastructure side and from the like ML or just the product side. From the infrastructure side, right, data comes in streams and doesn't necessarily show up to our door in a nice glue table. It might come in a Kafka stream, I don't know, something like that. So how do we build systems that allow the data ingestions to use the same underlying infrastructure? That's hard. From a product perspective, a lot of the times when you're doing online or live inference, you might get some lag or delayed feedback, what the customer chose to do with those predictions, for example. Whereas in the offline setting, you already have all of the data, it doesn't change. And there's no concept of lag. So in that case, right, what do you do? How do your algorithms differ? How does your data ingestion differ? A lot of questions there. The other thing is that, as you can see, right, this modeling or training algo, right, is like one little rectangle in this whole diagram. There are a lot of other components, from data ingestion to inference, and something that's super important in ML, just in software in general, is to version all of these artifacts and components. And this can get very complicated very quickly, right? And that think about when you train models, right? You imagine the number of like trained binaries. Imagine if you checkpointed everything you trained at least like 100 times. You come up with a bunch of trained binaries while you're doing one data science project, because this field is like very highly iterative by nature. How do you store and manage and basically have a clean way of accessing all of these artifacts? That's super hard to do. There are a lot of open source frameworks, DVC, MLflow, etc., for these kinds of problems. But at the end of the day, when you have so much data and so many artifacts sitting in your databases, it can be hard to navigate through all of that. And for requirements for a technical system, as shown on the previous slide, scalability and reproducibility is super important. Like, how do you grow project? How do you add projects to that kind of system? Fortunately, in a system like this, right, it would just be adding a new rectangle here as a new training job if we were to work on another ML project. And then how do you reproduce that, right? If somebody else is onboarded to your team, how did they actually get the same results? I talked about versioning the data, models, and artifacts, which involve train, evaluation, and test sets, the actual model binary, model parameters and hyperparameters, metrics, right? One key thing that I realized at my startup is, okay, I saved all of my model binaries so I could version them, but then I looked in the database and they're all joblib files, and I had no way of diffing them because obviously the parameters were different, but were they semantically different? Were the metrics produced by these models actually different? So I ended up having to also version the metrics, etc. And here my bottom line is creating a prediction, right, in a forward pass is pretty easy once you have a model. But once you have an ML pipeline that consists of multiple models maybe, or you've staged multiple different kinds of trained of similar architecture to production, backtracing that kind of prediction can be very challenging. For example, if you look and you realize that you have a mistake or a prediction mistake from 2 months ago, how do you find all of the artifacts and model versions and everything around your system 2 months ago, and then do that forward pass to reproduce the results? That can be very hard when you have so many different artifacts. The other thing is, I'll allude to this later, but every bullet point here practically has its own tool, over 200 MLOps tools that I have read about, or at least I read an article that talked about them. And this can be extremely complex to manage and very tedious and tiresome. So lots of issues out here. I'll go through a small case study. I know I talked at you a lot about a lot of these problems, but kind of like looking at an example of a failure in practice was very illuminating to me. And in this case study, I found the publicly available New York taxi cab trip dataset. It's a tabular dataset where each record corresponds to a taxi ride. And it includes features like pickup and drop-off times, number of passengers, trip distance, the pickup and drop-off location zones, and then the fare, toll, and tip amounts around this. It has monthly files from January 2009 to June 2020. It's a lot of data. I think I calculated back of the envelope calculation with each month was about 1 gigabyte of data to give us over 100 gigabytes. So already we have to use a cluster in some way if we're going to somehow leverage all of this data. So for this exercise, I just wrote a notebook. It's on my GitHub. I'll talk about it at the end, but I just trained and evaluated a model to predict whether the user gave a large tip. And I used deploy here in quotes to show like when you have that trained model and you've evaluated it on an evaluation set, and then you simulate live inference, like you can still get a really big performance drop. And why is very unclear, and how do you mitigate those damages is also very clear. In my tutorial, I use Python, Dask. I use this on a GPU. And the goal of this exercise really is to demonstrate what can go wrong post-deployment. Cool. So from the modeling side, let X be, basically I'm training a random forest model on this data set. And the goal of this classifier, basically we're training a classifier to predict whether the user gave a high tip. And I define a high tip as the tip amount is at least 20% of the total fare amount. I use the Dask random forest classifier so that I can iterate fast. I didn't do any hyperparameter tuning. Yeah, it was 100 estimators and a max depth of 10. And the thing here was I trained on January 2020, that month of data. I validated this model on February 2020, meaning hopefully the metric achieved was similar to the metric achieved on the train set. Sorry. And then I simulated deployment starting March 2020. There's no hyperparameter tuning here, so I did not have a whole data validation set. You were to do hyperparameter tuning, which you should, then you should have a holdout validation set to validate those hyperparameters. I measured the F1 score for the metric. I'm going to assume that people are familiar with precision and recall, and the F1 score is just a combination of precision and recall. At a high level, right, a higher F1 score is better because we want to have few false positives and few false negatives. So here's some of the code is in my GitHub, but essentially walking through this, read the data set, January 2020 data. There's 11 features in here around some of the stuff that I mentioned in previous slide. I trained a random forest classifier. Some of the syntax is a little bit different from Python because I use Dask, or sorry, is a little bit different from Pandas because I use Dask, but hopefully it's still readable. Featurizing and fitting the model. I don't do any data cleaning here whatsoever, so please don't call me out on that yet. And then the classifier's F1 score on the train set is 66.8%, which is not great, but for the sake of the tutorial, moving forward. And then evaluating on the test set, which is February here, we get a very similar F1 score, which in theory sounds great, accomplishes everything that we've been taught in school or in academic settings, right? Like make sure you don't have any leakage, especially in time series. Make sure you're not learning from the future or anything. So there's a clean separation here. And then, so caveats in here, as I mentioned, we didn't do any hyperparameter tuning. It's unclear, right, if this classification problem is actually valuable from a business context. So, and it's also unclear what the ROI would map to if we were to actually do this in an industry setting. But for the sake of the tutorial, let's just move on to simulating the deployment. So imagine it's March 2020, and I guess COVID kind of hits this month, so we'll probably see that somewhere. But we released our model into the world because we've trained and validated it. And there are a lot of infra challenges around this that I will get into. And also, it might be the case that we experience data lag, where the data comes into our databases after some lag. So really, on March 1st, 2020, we might not have all of the data until, I don't know, the end of February 29th. But for the sake of this tutorial, let's just imagine that there is no lag. Another consideration for these production ML systems are, do you want to do streaming or batch inference? And one thing is, for this tutorial, I will simulate inference on each record as it comes in a stream, but then I will compute metrics in a batch because every month has around 10 million, or 6 or 7 million rows, I believe. And in practice, of course, for both of these, you need to have infrastructure considerations. Yes. First challenge that I alluded to before is having lag. We don't have lag in this example, but I do want to highlight it because it's something that I've seen in almost every applied ML project that I've done in industry. And there are many types of lag, one being feature lag, which is our system only learns about the record or ingests the record, learns about the ride, taxi ride in this case, well after it has occurred. It could be anything from like days to weeks to months. On one project that I worked on, the lag was 6 months, which made it extremely hard to do any relevant time series ML. Another thing is label lag, which is maybe our system only learns of the label well after the ride has occurred. And this is very common whenever you're building something like recommender models or a system in which the user actually interacts with it, because, or for many reasons. And another thing that's challenging about using the user's interactions as a label is your model has kind of biased those labels. So those labels might come from a different distribution than before you deployed that model. So how do you tease out the effect of your model on the user's behavior and then just their generic everyday behavior? This is very hard to do, especially at scale. And of course, when dealing with lag, the evaluation metric is inherently lagging. And at training time, the model cannot reflect the most recent time, as I mentioned before. But for this exercise, we're lucky all of this is offline, and we're just simulating something offline. So here we are simulating the live inference. I'm loading March, pre-processing it. The way that I compute the metrics essentially is to sort values by the date ascending and then compute like a rolling F1 score, you could imagine, which is essentially the F1 score for all of the records on or before that row. I also compute a daily aggregate of the F1 score, which is if I looked at each day in isolation, what would be the F1 score for all of those rows. And what happens whenever I compute that for every day in March, I don't think we got the last day in March, but that's fine. So recall that our F1 score for January and February was around 66%. Awesome. And it's similar if you look at the recall score for all of March, it's 65.95%. But if you look at the day, or basically if you look at the daily F1 for each one of these days, right, you can see that there's pretty high variance. And then towards the end of the month, the F1 score drops like crazy to 50%, 53%, and 57%. So a lot of things came up for me whenever I was diving into these, right? One is the large discrepancy between the rolling metric and the daily metric. Why is this the case? This is a red flag, especially because imagine we were like simulating this live deployment. If we weren't tracking the daily F1, we would have no idea that our model was actually degrading in performance over time. What you monitor is extremely important for this reason, because otherwise you could imagine one day randomly, maybe in the middle of April, we might just like have a low rolling F1, and that would ring a lot of bells, and we could have traced that back to some issue or something in the data had we been monitoring a more granular or daily specific metric. You'll also see the visible effect, right, of COVID on this taxi data. I imagine people were not riding in taxis as much. I imagine they were not tipping the drivers, I guess, a lot. But it's very interesting to kind of see this performance degradation. And if you evaluate that same model on following months, so for example, April, May, and June, you can see that the F1 score does decrease. Remember that it was 66%. It was 0.66 on January and February, and it just goes down over time, becomes more high variance. You can attribute maybe a lot of it to COVID, but at the end of the day, even though maybe you have a hypothesis for why the model isn't performing well, you still need to have a high performing model, right? And maybe there's a lot of data science things you can do, like add features or whatever, but you still have the model performance degradation, right? And how do you go about debugging it? Or what does that even mean, right? What does debugging mean? Do you, I don't know, look into the data and see if something is wrong there? Do you retrain the model? Do you change the kind of metric, or do you change the classification problem? A lot of these questions are up in the air. Really, it's what the solution is something you'd have to discuss with a lot of the stakeholders on the project. But now we'll go into a lot of the challenges, right? So one thing is, right, as we alluded to before, especially when COVID happened, right, data drifts over time, where maybe data changes over time, and maybe the models will need to be retrained to reflect such a drift. But how often do you retrain the model? When do you retrain the model? If I retrain my model like thousands of times a day, which is like what Netflix or Uber or something like do, retraining adds complexity to the system, right? And all of a sudden I have way more artifacts that are versioned, way more model binaries that are versioned, data sets that are versioned, everything I have to keep track of. And backtracing, of course, is incredibly difficult when you have all of these things. Retraining can also be expensive in terms of compute, time, energy. And another thing is, how do you know when the data has drifted? And I'll talk about a paper here that Failing Loudly essentially is the name of the paper. It's a study of methods for detecting dataset shift. Maybe there's a way to employ statistical techniques to quantify the distribution shift in a way. And this paper presents a framework, right? Like you have two different distributions of data, and you want to see how similar, or you want to know if they're statistically significantly different. They propose some dimensionality reduction on the data, and then they run some two-sample statistical tests, and then see like what is the p-value as a result? Is there a significant difference? And okay, maybe we can apply this method to our data. I skipped the dimensionality reduction step because we really only have 11 features. Their experiments were on MNIST and CFAR, so I imagine that they need more, dimensionality reduction. They also claim that multiple univariate testing seems to offer comparable performance to multivariate testing. So maybe it's specific to images or whatever they were doing. Regardless, I just essentially will run a two-sided KS test, which is a form of multiple univariate testing. And at a high level, you don't need to know like all the stats about this. It works for continuous data. It's a non-parametric test. And I know this is the supremum of basically, so it's essentially the largest difference between two different cumulative density functions. And to explain that a little bit further, imagine we have two CDFs here on this screen. The KS test statistic is basically, if I were to run a line, like a vertical line throughout the graph, and compute the difference between the two curves, the KS test statistic is that largest difference. So maybe that is around like when x here is equal to negative 0.3 or something. I don't know. But you can imagine it's like this big difference here. In relation to the number of samples in the empirical distribution, you can compute the p-value and figure out if you want to reject the null hypothesis or not. So let's say I do this. I use the SciPy stats library, and I run the two-sided KS test on the train, or on two different distributions of data, basically for each feature. And for this example, I just compared the January and February data sets. And we know here that the metric is similar, and we could also compute the means and standard deviations. And I didn't include that here. I probably should. But we don't expect this to be significantly different, or we don't want it to be significantly different. But if we run the two-sided KS test, we'll see that the p-values are so incredibly small for each one of the features, maybe except for pickup minute. I don't know. But how useful is this? If I look at the output for each one of these features, looking at the test statistic in itself can be hard to interpret because you kind of need to know the scale of the data that you are, or the range of the feature values that you're working with, unless you normalize it or do something like that. But here, like looking at the p-value, right? They're very small. Just by normal, like if you take an intro stats class, you would say, yes, this is statistically significant. They're different. But in practice, right, when we're working with super large data sets, we get really, really low p-values just because there are, tens of millions of data points that we're comparing. So bottom line is this method, right, could have a high false positive rate. It could flag data drift even when the metric stays a similar performance, which would be very annoying, right, for an SRE or somebody to monitor. In my experience, I've used this a lot. It's flagged distributions as different more than I wanted to. And in the era of big data, right, we have so many data points. P-values are just not useful to look at. So still super open question really about what does distribution shift mean for these ML models, especially at scale, and how do we quantify that? Cool. And then the last couple of challenges I'll dive into. We saw the performance degradation. Maybe we want to establish more confidence in our training and evaluation pipelines, especially with time series data. There's no use evaluating just one model or validating that model. We want to validate the process of training and evaluating models, assuming we want to validate like the architecture choice, not necessarily trained model binary. So maybe that means we have rolling train and validation sets. Maybe that means I train on January, evaluate on the last week in January, and then deploy on March. Then deploy on February. Then I train on February, deploy on March, train on March, deploy on April, so forth. And maybe this means we only promote an architecture to production if each trained model achieves whatever acceptance criteria on its corresponding validation set. But this can get complicated quickly, right? Like as time goes on, do I need to make sure that all of the train and validation sets have been passed? I maybe have years worth of data, maybe just 1 month was a fluke of data. When do I know to ignore it or to try to get good performance on that too? The other thing that's hard about this is the infrastructure needed, right, to do such automated retraining and tracing the lineage of these models. And Michelangelo, people have a pretty good blog post on that too. Challenge here also is collaboration, right? Not everyone is trained in ML speak, right? If the performance of the model drops, it's very, how do you explain that, right, to people who are interacting with your system that might not be technical? And I wrote this pretty recently, but I like to think about this a lot. When I say the phrase algorithm, I mean a series of steps that I control. And maybe everyone means this, but there's confusion because different stakeholders control different things, right? I, maybe as the ML practitioner, control the algorithm for how I train the model. I control the optimizer. I control the number of layers. If it's deep learning, I control all of these specific things. But for a client, right, if they're using my predictions, the algorithm for them is end to end. Like they give me data and whatever they receive is the algorithm, or the algorithm is the process of receiving that, right? So how do we kind of bridge the gap between different stakeholders? It's pretty challenging. ML is inherently probabilistic, right, which is very different from software. We know we will get predictions wrong, but we do not know what we will get wrong. And this is very hard to communicate to clients who are mainly experienced in SaaS, where they can assign every prediction equal weight, or they can assign every output of their SaaS or their software with equal weight. You can't necessarily do that in ML. Sometimes you'll be very confident and wrong. Sometimes you will be not very confident and right. We don't know. So finally, I've highlighted a lot of problems, and I think there are a lot of areas for future work. These are only just a few challenges, and there are many more around deep learning specifically, right? Imagine I am using deep learning based embeddings as features for downstream models. And maybe there's somebody who owns that like embeddings model or transformer model. If somebody updates those upstream embeddings, then do all of the downstream data scientists need to immediately change their models? Because that is quite hard to do in practice. And in practice, right, at these companies, they'll have different forks of the embedding models, and to the point where basically every data scientist is working off their own fork. And this can get very hard to resolve pretty fast. Another very good paper that I cited here, the whole concept of underspecified pipelines can pose threats. Imagine, like in basic linear algebra terms, imagine you are solving an underdetermined system of equations, right? You could, two different models or two different solutions. This basically, the system of equations can have infinitely many solutions. So you could have two different solutions that achieve similar test set performance, and then when deployed out in the world on different data, who knows, could be extremely varying performance difference by nature. And deep learning is very susceptible to this, especially with all these over-parameterized models. Tooling and MLOps is also generally a can of worms. There's almost 300 MLOps tools that we know of, and more than 180 startups. Pretty wild to me, and I'm really just fatigued thinking about more tools at this point. And I think at a minimum, really in this field, we need a culture shift. Maybe that's assigning less hype to fancy models, or maybe that's celebrating the concept of data in just as much as modeling, right? Like a lot of the times, iterating on the data, adding new features, cleaning the data can give us more reliable performance in a deployment setting, rather than just, I don't know, messing around with model architecture, hyperparameters, and seeing what happens. And there's a lot to learn from the software industry in terms of modularity, functional components, how to debug, how to monitor, etc. Great. So I think that concludes the talk really for now. The code is on my GitHub, but it's not documented at all, so I'll get to it, I promise. The slides are also on there. I'll post them. You can also contact me on social media. I like to write, so I love when people read it. And feel free to email me if you have any questions. Otherwise, thank you.